Hello students. As you know, two main classes of aromatic substitution are there. One is electrophilic substitution, and another is nucleophilic substitution reaction. This lesson is concerned with reaction on a benzene ring, and in particular electrophilic aromatic substitution reaction. In content, we will cover Introduction, Aranium ion mechanism, and its energy profile diagram, orientation and reactivity, ortho-para ratio, and ipso attack. Introduction. What is electrophilic aromatic substitution? Electrophilic aromatic substitution reactions is a organic reaction, in which an atom attached to an aromatic ring is replaced with an electrophile. The displaced atom, or group is, usually a hydrogen atom. Examples of such reactions include aromatic nitration, aromatic sulfonations, and Friedel-Crafts reactions. It is important to note that the aromaticity of the aromatic compound is preserved in electrophilic aromatic substitutions. Therefore, these reactions can be used to obtain aryl halides from aromatic rings and halogens. In electrophilic substitutions, a positive ion attacked the aromatic ring because of the high electron density at the aromatic ring, which leads to its reactivity as a Lewis base, depending on the positive species. In electrophilic substitutions, the most important leaving groups are those that can best exist without the pair of electrons necessary to fill the outer shell, that is, the weakest Lewis acids. Now let us come to the steps involved in aranium ion mechanism. What is aranium ion? Aranium ion is basically an intermediate, which is involved in the electrophilic aromatic substitution reaction. So, the mechanism of aromatic electrophilic substitution is known as aranium ion mechanism. Electrophilic substitution reactions generally proceed via two-step mechanism. Number 1, the formation of a carbocation, which is an intermediate. Number 2, the removal of a proton from the intermediate to give the product. Step 1. The initial step is the attack of an electrophile. It may be a positive ion, or be a molecule that has a positive dipole, to give a carbocation, which is resonance-stabilized carbocation, or intermediate called aranium ion, which is also known as the Wieland intermediate. Although the Wieland intermediate, or aranium ion, is stabilized by resonance, this step is accompanied by loss of aromaticity, so the energy of activation is high. This is the rate-determining step of the reaction, because of the disruption of aromaticity, and the reaction follows second-order kinetics. Now coming over to step 2. In the second step, the leaving group basically departs, leads to regeneration of aromatic stabilization, to give the substituted product. The second step is nearly always faster than the step 1, and the reaction is second order. Energy profile diagram. Aranium ion mechanism may be represented by its energy profile diagram. The rate of substitution at ortho, meta, and para position depend on the height of the energy barrier, that is, del G, between the reactant and transition state. The energy diagram of aranium ion mechanism shows that Step 1 is highly endothermic, and has a large ΔG. This step requires the loss of aromaticity of the stable benzene ring, which is highly unfavorable. The first step, being a slow step, is rate determining step. Step 2 is highly exothermic, and has a small ΔG. The ring regains its aromatic stabilization, which is a highly favorable process. Orientation and reactivity. The group already present on the benzene ring determines the position of upcoming electrophile, which is known as orientation, and the rate of reaction, whether the reaction will be slower or faster than the benzene itself, is known as reactivity. Groups that increase the reaction rate are called activating group, and those slow down the reaction rate are called deactivating group. When an electrophilic substitution reaction occur on a monosubstituted benzene ring, the new group may be directed primarily to the ortho, meta, or para position. Also, sometimes, a fourth type of substitution may be encountered, which is called ipso substitution. See the diagram, which is a special case of electrophilic aromatic substitution, where the leaving group is not hydrogen, but the original substituent itself. The orientation and reactivity effects are explained on the basis of resonance and field effects of each group on the stability of the intermediate aranium ion. The groups that increase the reaction rate are called activating groups, and those that slow down are called deactivating groups. The groups, according to their influence on both reactivity and orientation, substituents are classified into three categories. First one is ortho-para directing and activating group. If a group of this category is already present on the benzene ring, then the incoming group is attached to ortho and para position. This is called activation of the benzene ring. Second is the meta-directing and deactivating group. If a group of this category is already present on the benzene ring, then the incoming group is attached to meta position. This is called deactivation of benzene ring. Third category is ortho-para directing and deactivating group. If a group of this category is already present on the benzene ring, then the incoming group is attached to ortho and para position, but they deactivate the benzene ring. This is the activating and deactivating effects of some common functional group. See the diagram. Here the pink portion are the ortho-para directing group, which are activating substituent. Example of such groups are amino, hydroxy, alkazy, acylamino, acyloxy, alkyl, and phenyl. Here the blue portion are meta-directing groups, which are deactivating substituent. Example of such groups are carboxy, carboxamido, carbolcazy, acyl group, sulfonic acid, cyano group and nitro group. But one exception is there, though halogen atom, which belongs to group 17, are ortho-para directing group, but they are deactivating substituent. Example: fluorine, chlorine, bromine, iodine. The three possible ions from the incorporation of electrophile, that is, Y, at the ortho, meta, and para positions, are shown below. Here, each aranium ion has a positive charge in the benzene ring. If the group Z has an electron donating effect, then it should stabilize the aranium ion. On the other hand, electron withdrawing effect, increase the positive charge on the ring, and destabilize the aranium ion. Some substituents have a pair of unshared electrons, that may be contributed toward the ring. In this diagram, ortho and para aranium ions have a fourth resonance contribution. That means, we can draw an extra structure, in case of ortho and para substitution. The stability of these two ions is increased by the extra form, because it is more stable than the others, and makes a greater contribution to the hybrid. See the structure, C and D, both the structure has a complete octet, while all the other forms have one carbon atom with a sextet. No corresponding form can be drawn for the meta-isomer. During ortho and para substitution, structure A and B are obtained respectively, where positive charge is present, at ipso carbon, that is the carbon on which Z group is present. But, such structure are not obtained in meta-substitution. Substitution. Ortho-para ratio. When an ortho-para directing group is on a benzene ring, it is usually difficult to predict how much of the product will be ortho-isomer, and how much will be the para-isomer. Since there are two ortho positions, and only one para position, it may be expected that ortho and para isomer should be formed in 2:1 ratio, and these proportions can depend greatly on the reaction conditions. So basically it is a ratio of products formed when a benzene ring with activating group undergo electrophilic aromatic substitution. For example, if the substituent is activating group like CH3, which size is normal, then ortho product is major product. See the example of nitration of toluene. When toluene undergo nitration, it gives 2 product, 58% of the ortho-nitrotoluene, and 37% of the para-nitrotoluene. Para-isomer will be formed preferentially, if either the substituent on the ring, or the incoming electrophile size is larger. Several factors like steric hindrance, polar effect of the substituent, solvent effect, temperature etc., affect the ortho-para ratio. An important factor, which affect the ortho-para ratio, is steric effect. If either the size of group on the benzene ring, or the size of group on the electrophile is large, then the steric hindrance inhibits the formation of ortho product, and increases the amount of para-isomer. An example may be seen in the nitration of tertiary butyl benzene. The bulkier tertiary butyl group gives 16% of the ortho product and 73% of the para product. Another important factor, which affect the ortho-para ration is inductive effect. See here, if halobenzene undergo nitration, then these are the ortho product, given by the different halogens. As we know, fluorine, which has greater inductive effect, out of 4 halogens, has greater deactivating effect at ortho position, compared to para position. Fluorine has greater deactivating effect than chlorine, and deactivating effect of chlorine is greater than bromine, which has greater effect than that of iodine. Therefore, iodobenzene gives largest amount of ortho product, as compared to others halobenzene. Now let us come to ipso attack. There is a possibility of electrophilic attack at the ring carbon atom, to which the substituent are attached, that is X. So, the substitution of the original substituent by the electrophile is termed as ipso-substitution. Now you can see here, incoming electrophile, that is E+, replace the original X+. Ipso-substitution is promoted by substituent, that is X, which can form a stable X+ cation after attack by the electrophile, and they are good leaving group. Thus, substituents such like bromine, iodine, at alkyl group, usually secondary and tertiary alkyls, can form stable carbocation when undergo electrophilic aromatic substitution reaction, predominantly forming ipso product. These are some example of ipso substitution. See the first example. From the name itself, de means removal. So here, silyl group will remove by the bromine atom. Bromonium electrophile, substitute trimethylsilyl group. See the reaction, when trimethylsilyl derivative of carboxylic acid, react with Br2, which will generate electrophile, that is Br+. Then the bromonium electrophile remove entire trimethylsilyl group, and take that position. So this is a ipso substitution. Now come to second example. Similarly, here also, sulfonyl group is removed by protons, means by H+. So it is called proto-desulfonylation. See the second reaction, benzene sulfonic acid, is treated with dilute acid. Here the electrophile is H+, that means proton, and it will remove the entire sulfonic acid group, not the hydrogen. So it is called ipso substitution reaction. And in the product, hydrogen take the position of sulfonic acid, by the removal of acid, that is H2SO4. Thank you.